All right, here we go. So this is a history of the speed of light and the motion of Earth, and how the theories that were put forward to explain why they couldn't quite get the measurements that they were looking for in regards to the velocity of the Earth relative to a luminiferous ether. So starting with 1770 or 1727, there was a guy named James Bradley who was taking zenith measurements of a star. And that just means he was looking through a telescope that's like looking straight up at 90 degrees. And the where his telescope was located, a star named Gamma Draconis was supposed to directly go right in the crosshair of that telescope. But the star would never quite be in the center of that. And so throughout the year, it would like fluctuate a little to the left, a little to the right, essentially. And so he marked the minimum and maximum dimensions of that, and it comes out to be 20 arc seconds throughout the year. And so they took that 20 arc seconds, and if you do the arctan of 30 kilometers a second over the speed of light, which is about 300 million meters per second, it comes out to be the same angle that was measured. It comes out to be 20.452 arc seconds. So everybody was super excited because this relationship using the constancy of the speed of light, or using that value and that ratio of Earth's velocity, that it gives the angle that was measured. So everyone was super excited because the only way that that could be produced is if there was something that was moving at 30 kilometers a second. And the boys had a specific ratio of how fast they thought the Earth was moving based off of Kepler's laws and Newtonian dynamics. So a quick introduction into those is Kepler's laws are a ratio of pi and the periodicity of how long, which just means how long it takes a planet to complete a circuit. So those give basically those give a an orbital circumference, right? So it was traveling this distance to complete a circuit, so it means it has to be going this fast. So when you work out those ratios with the Earth and the Sun, the either the Sun has to be moving at 30 kilometers a second around the Earth, or the Earth has to be moving 30 kilometers around the Sun for that ratio to hold a relationship. But that relationship alone is just mathematics. It's just a ratio of a periodicity in pi. So like that's not necessarily proof of anything, although it is like a conceptual model, right? Like how to relate the ratio to a distance and speed and all that. So then they introduced Newtonian dynamics. So they took the big G from Cavendish, and they took the mass of the Earth from Cavendish, and they algebraically reversed what the sun would have to be to produce the gravitational potential to complete the orbit. So what they found is basically you could derive Newton's laws from Kepler's laws. But there's a little trick that they don't really tell you about, and it's the mass in the equation when you do Newton's laws cancels out. So in GMM over R squared, the M's cancel out, the G is just a constant, and it falls off to a to the R's, which is a radius, which goes back to pi, and then of course the periodicity. So it literally falls back to the same thing as Kepler's, where it's just a ratio of a constant over with periodicity and pi. But it doesn't necessarily tell us anything physically meaningful, although the heliocentrists, have taken the fact that you could derive one from the other as like, oh my God, this must mean these are the values, and this must mean, this planet weighs this much and this much. This is how they came up with all these weights and stuff, because it's just a ratio of the first thing they started with moving outwards, right? So once they have all that, they make it all relative to the sun, yada yada, and then life continues. Everyone's happy, the Earth's in motion, and they have an actual first order measurement, which is a V over C relationship where the velocity, right, is directly proportional to the speed of light to produce that angle. So everyone was very pleased. But there was still one thing bothering the lads, because they were physicists and like, educated men at the time. So they were all aware of the fact that the measurement alone can't tell them definitively if the Earth is truly in motion. You have to do an experiment. You have to manipulate a variable here, because there could be a medium in motion between us and the starlight. The Earth could be stationary, right? The Earth could be moving slower, etc. And like I said, that medium could be like doing the rest of the work. So we have to do some sort of experiment to determine, uh, what is the cause of this ratio here, of this V over C producing this angle here, even though it closely matches or it exactly matches the 30 kilometers a second. So before we get into how they, or what experiments were conducted, we have to look at how they were conceptualizing light at the time. So at this time, there were two different theories of light. One was the emission theory, where light was treated as a little ballistic projectile. And the other one was the wave theory of light, where the luminiferous ether, this medium, is the medium that the waves are undulating in, right? So these lead to two different mathematical predictions, which we'll go over the history of here in a second. Starting with, who was first? Was it Foucault in 62, 51 for now? Okay, so in 1951, a guy named Fizeau did an experiment based off of a math equation given to him by a man named Fresnel. Fresnel had a hypothesis that the velocity of water that the velocity of light noted by this U character here would be equal to the speed of light over the refractive index plus or minus the velocity of the moving refractive index, whether you're going with or against will be addition or retardation. And then you have this coefficient over here, 1 over the inverse of the refractive index squared. His hypothesis is that there was an elastic ether, and the density of that ether inside of a translucent media was proportional to the square of its refractive index. So, and he derived this off of the same principle that they derive the speed of sound in a medium. They can do like, how fast does sound go in this gas? Well, it's the inverse of the density of the gas that will tell you how fast the wave will go. So under that exact same principle, he derived not only the speed of light for this medium, but how much the medium would drag light with it when it's in motion. So Fresnel was like, okay, well, let me run this and see what's up. So he comes up with the first interferometer. And what this is you have a light source. For this, they use sunlight, and it hits a beam splitter where the beam goes clockwise and counterclockwise around a circuit of the interferometer as it hits 45-degree angled mirrors to complete its circuit, where it gets recombined on the other side. Now, as you can see here through this configuration, the light that's moving with the flow will get velocity addition, and the light that's moving against it from the top here will receive retardation. And then when they recombine, this light beam will be out of phase. Now, if the ether drag doesn't, if this hypothesis of this coefficient here, this 1 over the square of the refractive index, doesn't mean anything, then this light beam will recombine and it'll still be in phase, just minus the refractive index, right? So when it recombines, there's not going to be like a fringe displacement that's proportional to any sort of velocity, right? But what they measured was that the light was out of phase by 44% of the velocity of the moving water going with and 44% going against. So the hypothesis that there was an elastic medium in the translucent material that was proportional to the square of the refractive index was substantiated. It was a valid measurement. It all worked out. So from that, they were like, okay, well, what can we do with this? Well, a couple of things still needed to be worked out, and that was in regards to the emission theory and the undulatory theory here, because for some reason this it still wasn't settled yet, even though the emission theory predicts that water, or that light and water would the velocity of light would increase because they were multiplying by the refractive index instead of dividing. So that creates an acceleration as a function of the refractive index instead of reducing it. So there was still some discrepancy there for, like, as we're told, right? It's like, I don't know how they didn't conclusively figure it out from this alone. But anyway,
Can I ask a quick question?
Yeah, go ahead.
So when they did that experiment you were just at, and they shot it against the water and with the water, did it end up in the same phase at the end?
No, it was out of phase by the exact amount of or not exact amount, but by a ratio of the velocity predicted by the equation.
Gotcha. So the emission theory projected it would be even more. Is that what you were saying?
No, the emission theory would predict it would be less because the light would accelerate.
Gotcha. Okay. Okay.
So yeah, if you can imagine like these see these black gaps here in between the colored gaps. So the wave theory would predict that these gaps would be bigger. The emission theory would predict that these are smaller, thinner.
Gotcha. Okay.
Because what you can do is you actually measure the distance between this gap, like the black side here, starting here, and where the black gap ends. You measure that distance with a micrometer, which is just a thin wire that's 1/1,000,000th of a meter in thickness. And however many of those are, the distance of that, the square of that distance is proportional to the velocity. That's how interferometry and fringes work. So like there's a direct relationship to these fringes. So like they knew the exact amount of velocity that would come out of this when they math it out and finish everything out. They're like, okay, we had the water moving this fast. It was out of place by this much of a gap. We square that gap. Oh, it comes out to be exactly how fast the water was moving. Or well, 44% less because like I said, it's an 88% ratio, 44% with, 44% against. So they worked all that out in 1852. And then they were still, I guess, puzzled or whatever. And they were like, I don't know, maybe emission theory is legit skis. Let's do a test. So here's where Foucault comes in, 1862. He has a light source. He has a viewing surface for the reflections to go back to. He has a mirror that's rotatable. And he has a mirror to reflect it off of. So what's going to happen here is light source is going to shoot at the mirror. The mirror will either be rotating or it'll be stationary. It'll reflect off of this small mirror. It'll come back. And then this angle here that it hits on the viewing surface will be will tell you which theory is correct in the behavior of light, because what they were trying to do is establish if you could use light to measure motion. So in this instance, this diagram here is like slightly off. These are actually the rotating mirror was perpendicular to the light coming in, so it's kind of like off here at an angle. But just imagine that this is straight perpendicular to it, just like at a straight 90, like making a straight elbow angle for the reflection. But anyway, what would happen is if light is independent of motion, then when this mirror is rotating, the light would hit this mirror, reflect back, and then it'll hit this viewing surface, and it won't change. It'll be as if the mirror is stationary, right? The angle will be in the exact same spot as the air spot. Now, what happened was when the mirror rotates, even in air, the angle increases. So that's like problem number one for them. And then, but remember, there's two theories here about what would happen if we introduce a medium. So Foucault introduced a tube filled with water between the mirror that reflects back to the rotating mirror, which leads back to the viewing surface. And so the emission theory, predicting that the light would accelerate by a function of the refractive index, would predict that the angle gets smaller. So the normal, or we're going to call the error the normal. The normal would be right here at this location. The emission theory predicts that it gets smaller from the normal. And the undulatory theory, the wave theory, predicted that it would deflect away from it. It would get bigger as a function of the velocity and the slowing of the light, because the more the light has to slow down in the tube, the more the mirror can rotate, which creates a bigger distance from when it left the mirror. So that's going to make the angle bigger. And that's exactly what was translated. When my boy added the water, the angle increased. So it falsified the emission theory. It showed that that is likely not true, right? Because it just, experimentally didn't happen. And what was predicted by the undulatory theory did happen. Now, keep in mind, in modern times, relativity says that the velocity of light is independent of the refractive. It's frame independent. It doesn't matter if there's a refractive index or not. In fact, for the relativistic calculation for aberration, which is the thing that Bradley guy measured, right? They don't even use the refractive index when they consider Airy's failure. So what relativity predicts in this experiment, so like this experiment alone falsifies relativity on the face of it, because relativity would predict that the speed of light is independent of the light source, so there's not going to be any real timing difference when you add the medium. And if there's not any timing difference, then it doesn't matter how much this mirror rotates because the light's going at the same speed. But what happens is the light is slowed down, the angle is increased. So the speed of light is not frame independent, right? It literally a real timing difference is created when the light is moving through the water with respect to the lab frame, which is exactly antithetical to the theory of relativity on the face of it.
So there goes the prediction, the particle theory and relativity all in one experiment.
This zips up both of them.
And this is like getting two birds stoned at once.
2 birds, 1 stone. 2 birds, 1 stone. Because this is what we have here, right? In the original Fizeau experiment, we have longitudinal drag, right? And then for something like this Bradley guy, what he was measuring, right? This would be transverse. So the motion of Earth is going long ways here, longitudinally, and the light is coming in perpendicular to that motion. So this would be a transverse drag effect. Now, they had experimentally verified the longitudinal drag. And so this verifies the transverse method. Because like I said, this mirror is actually 45 degrees relative to the thing. It's just this particular diagram makes it, just for ease of viewing, has it arranged like this. But the significance of this is that this is a transverse relationship here for the motion relative to the light source. Extremely important, because what this means is this is a miniature Airy's failure experiment. Okay, so like I said, we already covered we just covered the transverse aspect of the situation here. Later in 1971 and 76, this transverse effect was also measured by a guy named R.V. Jones, who used a rotating plastic disc and a light source. So the light source comes in perpendicular to the plastic disc. Plastic disc is rotating transversely to the light source. Relativity predicts that there's not going to be any change. It's going to just follow this dotted line here and have no deviations. What was experimentally measured is a positive angle change with respect to the rotation rate. So even though this would turn clockwise and counterclockwise, it's always a positive angle when it's transverse.
So it's essentially doing what Foucault's water tube was doing.
Yes. 1-to-1.
And you can see it in that diagram right there, that it slows it down enough due to the medium so that it gets, there's an angle change.
Yep.
Ideal. Yeah.
Yes, sir.
Okay.
Yep. And also the velocity of the medium is translated in this, not just the refractive index. That's the other important part of that. But so anyway, they experimentally knew off the riff that what would happen, right? So it was proposed like 100 years before Airy even did this by some Jesuit that was like, I'm not sure if the Earth's in motion or not. Maybe we could use water and a telescope to figure this out. And it took 100 years for the boys to get together and do it. So a guy named Clinkerfuse, before Airy, filled his telescope with turpentine and said, I measured an angle increase change, boys. Check it out. Heliocentrism's definitely real. And Airy was like, oh, well, Clinkerfuse is a man of repute, so I will also do the experiment and confirm this, as I am the astronomer royal of the Royal Astronomical Society. It's my duty to, tell get everyone the best measurements possible. So he has the boys whip up his zenith mount here, which is a engineering marvel at the time. Even to this day, it's still pretty badass. But anyway, so what he was doing with this was the same thing that Bradley was doing, taking zenith measurements of stars, where they would be expected to be 90 degrees overhead. And what he found was when he added water to this telescope and took the measurements, the starlight did not change. So what does it mean if we go back to this? What would that have to mean in order for this to make sense? You would have to say that the Earth, the observer, is stationary, and the light is already coming in at an angle. So if the light is already coming in at an angle and you add water to it, right, and it's directly at 90 degrees to that incoming water, and there's no change to it, the only thing that would make sense is that the light is coming in with a horizontal velocity component to it. It's coming in with a drift. And that's what the implication of this measurement is. So when Airy says that the aberration in air is the same as aberration in water, people nowadays mistakenly say, "Oh, well, that means that the Earth's in motion." That's not what that means. That means that the angle was unchanged. That's all that means. You have to now interpret what that means, right? Airy's not going to tell you that his whole world belief is falsified. He's just reporting the results. So logically, if the Earth is in motion, the Earth is the thing that's dynamically in motion, then the angle would have to increase. But it didn't, right? It didn't get smaller, it didn't get bigger. So the only thing that could satisfy that is the Earth is stationary with respect to the moving sky. But they were dissatisfied with that. So they came up with the theory of relativity to explain that. And the way that relativity explains this is that because you're in motion and the sun's in motion, it's the light wave that comes in slightly tilted. So when you observe it, it just looks that way as if you're stationary. And because relativity is a theory of reciprocal transformations, you take the measurement that you took in the lab, which has the implication that you're stationary, and you do a transformation to this, or what you would do is you would say that we're stationary on Earth measuring no change. But if we could see an observer on the sun being in motion, he would see the angle change. And then you transform to the sun position, make the sun stationary, then the Earth's in motion, and then we would see the angle change. Like, it sounds retarded, but that's the way that they came up with
It
trying
sounds
to
retarded, and that's the comment that you made earlier about, just put somebody where they're not.
Dude, yeah, their whole entire thing is based off of that.
Or they invoke somebody like somebody like traveling at the speed of light. It's like, okay, now we're getting into thought experiment,
right,
where somebody's actually capable of moving at the speed of light. You can't falsify that. So yeah. That's
Quick question.
Yeah.
Did Clinker Fuse and Aries get different conclusions?
Yes. So Clinker Fuse said that he measured the increase, and Airy was like, okay, let me see if I can repeat that. And then he did, like, he was like, it didn't change at all, and nobody else has ever done it again.
Is turpentine like thicker than water?
Great question. No.
Oh, okay.
His angle predicted increase was much smaller. So Airy's was like, let me use water, because it'll slow it down 0.75 or to 0.75 C, and that will give us a nice increase. Because remember, the regular angle was 20 point something arc seconds, and then if you add water to this, it becomes like 28 arc seconds, something like that. I have a spreadsheet here. It comes out to 27 arc seconds if you add water. So it's a very significant measurable difference there that should have happened. Whereas I think Clinker Fuse, if you add turpentine, it comes out to, it would be like 20 point. I can't remember. Actually, wait, no, it would be 26, I think. But yeah, it would be like 26 arc seconds. So Airy just went for like a bigger one. It's 1 arc minute bigger.
Gotcha.
But I'm sorry, arc seconds. Anyway. Let's see, where were we at here? Okay, so relativity tries to answer it, through that way, but we'll get to relativity here in a second. The big thing to note is that we started with a V over C relationship. We started with, and this is what you would call, because this is V over C directly proportional, this is what you would call an absolute measurement of velocity. This would be, this is what they're asserting, that this is proof of the Earth in motion. Now, remember, in modern times, relativity says all motion is relative and you can't really know. So, they use this as the backbone of the proof of their theory. And then when they go to make other and when they go to substantiate the velocity by actually manipulating variables, they don't get it. And they're like, oh, well, you know what? You actually can't tell. So that's, I mean, that's, if that's not the ultimate goalpost move slash just, you know, outright lie, I don't know what is.
Yeah, that don't make sense.
Nope, completely incoherent. So let's see here. Okay, so they did this, and that's pretty. This was pretty damning, but still not the worst, right? Because maybe there's hope. So they started coming up with these theories that the ether theory started changing, and they were basically coming up with ad hoc explanations as to how the ether was dragging the light in such a way that it was creating, that it was like basically removing the first order effect of velocity. So they were like, okay, in air, there's not a big enough ether density to for the drag to be affected. And then when we add water, right, it's like too dense, or maybe like maybe it's dragging, maybe it's like maybe the ether is bouncing around in the interferometer or the telescope, and it's carrying the light in the opposite direction of motion. That's the kind of stuff they started suggesting, because when they added water, like it was like a complete no-go. So they were like, okay, we can't measure first order relationships in the change of the speed of light with, you know, in velocity. So a man named Hoke came along right before Michelson-Morley, and he was like, okay, I'm going to build a Fazal style interferometer, you know, following this kind of configuration here with the light in the water. And he was like, okay, I'm going to have one of my arms have just be a tube of air. My other arm is going to be a tube of water. The water is going to be stationary, but the Earth's moving at, you know, 30 kilometers a second. So this tube of water has a 30-kilometer velocity potential with it when it's parallel to the direction of motion. So when I'm aligned to the direction of motion, this has a 30-kilometer velocity potential to it. And this one will be unchanged because the refractive index of air isn't strong enough to drag the, you know, it's not strong enough to drag the ether velocity with it to change it that much. So what he predicted was that, oh, and based on what they were saying about the, hold on, freak. It's, okay. So to explain why this measurement didn't go their way, Lorentz's theory was, you know, the reciprocal transformation theory, and Stokes, a man named Stokes, and Fresnel hypothesized that the light was being dragged in the opposite direction of the motion due to ether that was dislodged in the telescope, and it was canceling it out. So Hoke, thinking that he was like, you know, because you got to understand like the mindset of what their hypothesis was and why. Understand, like, isn't it like what? Why would anyone think this? So to think he was like compatible with the theory of explaining why there's no first order measurements, he predicted that the light in the tube in the water tube would be carried in the opposite direction. It would cancel out the effect, and there would actually be no change. So if the Earth is in motion, when he aligns this parallel and perpendicular to the direct, because he could rotate this, he predicted that there would be no change. And if his other, to falsify that hypothesis, to prove them wrong, right, he derived what the fringe would be if this light slowed down with its 30-kilometer velocity potential, et cetera, he derived what the fringe pattern would be if this light beam recombines and the Earth has that velocity, et cetera, right? Now, he got no change. So he was like, oh, dude, boys, I just verified Fazot and Fresnel's and Stokes' theory down to the millimeter, or millimeter, down to the wavelength. We're super pumped, right? And then Michelson came along. So real quick, this configuration here where the light beam enters here, it gets split in two different directions and recombines. This is a first order setup. Right now, so that was compatible with their understanding of like, okay, we can't measure first order stuff. So Michelson was like, this was their last ditch effort to try and measure the velocity of Earth by coming up with a configuration where the geometry was such that the light would be reflected there and back. So it would take like 2 trips. And they were thinking that during that second round trip back, that the ether effect that's canceling out the first order term wouldn't be able to cancel out the second order trip. So they predicted that the square of the velocity over the square of the speed of light times the distance traveled that light takes over the interferometer would produce this smaller proportional fringe to the velocity.
So
You
it's
have
the
any
final
questions?
boss of interferometers.
What's that?
It's like they tried to create the final boss of the interferometers to solve it all.
Yes.
Michelson-Morley. Yeah.
Yes. It's actually like ingenious, although their like logic was flawed because it's very obvious that the Earth isn't moving. But like this is like genius levels of like setup and like ingenuity here. So they math out what the timing difference would be, or like how the distance would change if the Earth is in motion, right? So like if I start this light now and it's going to complete this 11-meter circuit, how much is the Earth going to move in that time that it takes for light to complete this circuit? So he runs this series here, expands it out, and finds that once you get into anything higher than V over C squared, you're not going to be able to make any noticeable measurements. It's not going to matter. It becomes too small. So they were satisfied with their V squared over C squared, and they predicted that they would be able to measure a change in the wavelength down to the 100th of a wavelength. Now, they had the accuracy to do it down to a 10th because they could measure, this apparatus was sensitive enough to measure 2 kilometers a second and still be like within spec. So keep in mind, they were trying to measure 30, and they measured between 6 and 8, and their air tolerance was 2. So they were, well, this apparatus was like ready to go. So they derived. What's that?
They were the apparatus was over-engineered for the task at hand. It was like super sensitive, more than what it needed to be.
They crushed it. It was fantastic. Yeah. They did a great job. So like the first iteration, the apparatus was like attached to the ground, but there was too much ambient vibration. Once they added a mercury pool and a concrete slab, like forget about it, dude. They were ready to roll. Nice. So anyway, they derived what their fringe should be to correspond to the change in wavelength if the Earth has a velocity component of 30 kilometers a second. And then so for this configuration, instead of being parallel to the direction of motion, they thought that the transverse arm would experience ether drag. So they were looking for that drag in the transverse arm when they were rotating the apparatus. So like what you could do, so like same kind of, almost the exact same situation is here, except instead of completing a circuit, they just rotate the interferometer in a circle, and then the arms that are north to east will become south and west, so on and so forth as you rotate it. So what they predicted is, like, let's say that the east arm was in the direction of motion. They predicted that the change would be in the north arm, right? Because it would be dragged transversely to that motion. And what they measured in the fringes there was that the velocity component was, like I said, let's just call it 7 kilometers a second, because it'll be between one of those two, 6 and 8. So it comes out to 7 kilometers a second. And that's a definitive, like, no for heliocentrism, right? That is a positive measurement outside of their threshold for air, but not big enough for what they need to substantiate heliocentrism. So what they say at the end of their paper is like, hey, if there's any relative motion between the Earth and the luminiferous ether, it's not as much as we expected. Maybe we should do more experiments throughout the year and see if we can get some larger velocity components to be measured. And there was one other thing I wanted to add. Oh, right. So at the end of their paper, they say that if this measurement stands as is, Then the theory of Stokes and Fresnel fails to explain it because they would predict that the drag would cancel out and there wouldn't even be a second order measurement. And then or not of that magnitude anyway. And then the other theory, Lorentz's theory, the theory of reciprocal transformations, predicts no timing difference. So that theory also fails. So he said all three of those theories, well, all two of those theories fail, but proposed by three people. But anyway, if those measurements stand, so that's why they talk about Michelson-Morley nowadays as a null result. They measured a nil, they measured nothing, et cetera, et cetera. But the data is all right there in their paper. They measured over one fringe, which corresponds to corresponds to 7 kilometers a second. And they even stated that the other theories that would have been available to try and explain this if they actually measured a null would not be able to explain this because they didn't measure no change. So that's where relativity comes in, and Einstein's like, hey, we know that to the first order of small quantities, we can't tell if things are in motion. So I'm going to introduce this theory to explain why there was no second order effect, and that's link contraction and time dilation. The link contraction and time dilation are these really small second order terms. That's v squared over c squared that they try to apply to everything, and ignore first order measurements. But that is the baseline of the history of interferometry and these measurements and what they mean and their implications and how they work. So instead of doing like transformations, the way that we would interpret these is that the Earth is stationary with respect to a dynamic ether, and the ether velocity is what's producing the velocity boost or retardation with respect to the orientation of the interferometer throughout the day and year.
So the guy who used the apparatus, the interferometer that had water and air, that little diagram you drew.
Yeah.
That guy said he didn't measure any. He didn't get anything, and so that was proving that there's no like condensed ether in the water or whatever. Is that kind of what that showed, or?
No, this was him measuring no change in here was them confirming the idea that they couldn't measure a difference because of the condensed ether in the tube, and like maybe it was bouncing around and carrying it in the opposite direction.
Gotcha.
So like it sounds ass backwards, but if you look at it from their perspective, where the Earth's motion's already assumed, and like now they have to backwards figure out how the ether works into that. So they're that's why it doesn't make any sense as like, oh, I measured nothing, that must mean Earth's moving. But that was the
gotcha. Okay.
Yeah, but that was the mindset back then, to try and reconcile measurement with expectation.
And all the while, this is just, they can't let go of the fact, like it's 100% we're moving. So no matter what we measure, we're moving.
Right.
Sounds like it. It sounds like given that the Earth is moving.
Even though this is the experiment to test if the Earth is moving.
Right.
That's bizarre.
Right. It's the ultimate scientific fraud and reification. Like, this experiment is crazy, dude.
It's almost like Einstein was hired to come in and clean up the mess to keep the motion.
Well, what gets crazy with Einstein's theory, right, is Lorentz's theory of reciprocal transformations is a recycling of a guy named Voigt, who used the exact same transformations, assuming an elastic medium to create a timing and spacing within the waves with respect to that medium. And that's how he was explaining Doppler shift. So like the medium would create the timing and space, would compress the waves or let them expand as a function of velocity. And then Lorentz was like, okay, cool, I like that. Like, and Lorentz has even given Voigt full credit. So that's like the crazy thing about this is, even in there's documentation, which I should go and get, that show Lorentz giving Voigt credit, like admitting that this is like, yeah, this is a Voigt transformation, homie. And then so Einstein comes along, and then in his 1905 paper, he uses the exact same framework for his transformations to propose relativity theory. And he's like, yo, there's no ether here. That's why at the beginning of his paper, he makes this big point about how, an ether theory here would be superfluous because we're going to use reciprocal transformations between two observers with respect to a symmetrical midpoint between them. But we're not going to talk about that midpoint because that's an ether theory concept, but we don't need that. So we're not going to, fuck that midpoint. Don't ever talk to me about a midpoint, even though if something's rotating or a Wang interferometer comes along, like, yeah, we're going to use the midpoint. But obviously for right now, no midpoint, boys. And so the significance of that, though, right, is that Einstein didn't derive his theory under any new principles or anything, or like showing that how this is possible without invoking an arbitrary midpoint for it to be symmetrical to establish space-time symmetry. So all he did, right, was just recycle an ether theory that was proposed before another ether theory, and then tell everyone that there's no ether here.
Wow.
And he never gave Lorentz credit for it. And it's literally called a Lorentz transformation, which should be properly called a Voigt transformation. And even Lorentz said so as much. He was like, yeah, I mean, my boy Voigt did the same thing.
Yeah, it feels like all this proves the ether. Like you say, it's ass backwards. It's like the empirical data shows it's not moving. So let's figure out what this ether is doing. But instead, they go, well, we're moving, and we got to get rid of the ether.
Yeah. After definitive measurement with the wavelength thing, right? Because here they're like, they can measure the velocity down to the wavelength because they already established how it works with that relationship, how to make these measurements, the significance of them, how to interpret them. Like this equation here that they derived, this is the Sagnac equation, same exact one. Path length of light times the velocity in question over the speed and wavelength of light. That's the same exact equation. They nailed it. They knew exactly what they were doing. And then the Fizeau equation, they still use this same one today in ring laser gyroscopes for inertial navigation systems, because the gas inside the lasing chamber gets a preferred direction based on the electric current running through the tubes to start the laser. It creates a bias for the flow of gas inside of the tube, and there's literally a little baby Fresnel drag inside of it based off of the that preferred direction of flow. So they have to like subtract this out to zero out the instrument. So like all these effects that were discovered in the 1800s and derivations of timing differences with respect to a medium are literally used in everyday technology to this day.
You just got to look under the hood.
Yep. Exactly. So do you have any questions, sir?
No, that was really edifying.
Cool. All right. Well,
Yeah,
I'm gonna.
now we can
Oh,
see why they really kind of pumped up Einstein and in the media made him sound like he's this brilliant guy that, just gave us the most brilliant concept in physics. They totally just created Einstein as this phenomenon in the media and brainwashed us into believing that he was an absolute genius.
Like first celebrity scientist ever, like
yeah.
celebrity chef level.
Yeah. Exactly. And, he didn't even invent or derive E equals mc squared either. Like
No.
four other people did it before him, and
Yeah,
most
he hijacked
famously was like some Italian lad. I can't think of his name off the top of the dome, but he derived it under like completely different principles of like burning calories or something. It was insane. He derived it, and so Einstein comes along And he's like, oh yeah, A equals MC squared. And he doesn't even do that in the 1905 paper. He does it in a supplemental paper, and he doesn't even do the math right for that. It actually took a guy named Max von Lau to redo it for him, or Planck did it for him. I can't remember. One of those two lads ended up having to derive it for him. He actually never even derived it. He like resubmitted supplements to the theory like 3 or 4 different times, and none of them like derive it under the actual principles. So there was a guy named Herbert Ives who pointed this out in a couple of papers.
Didn't Henri Poincaré also have like a variation of relativity?
Oh, a space-time continuum? I think so. I'm not super familiar with what Poincaré was working on, but I've heard that he was also working on a space-time situation. But then he ended up not going through with it because he thought that it wasn't right to impose mathematics on nature in the way that they were doing.
Yeah, that's a trip.
He had like a philosophical gripe with it.
Yeah, I could see that. Taking Cartesian space and time, conceptual abstraction that we use to quantify motion and change, and turning it into something substantive that you could dilate, contract, bend.
Right.
Like material is just like so wonky.
Math wizardry.
Yeah.
And disingenuous.
Especially when it's equivalent to an ether theory that uses an absolute reference point. Because although the space-time, the way that Einstein worded it or whatever, like that's cool and all, but it still takes a symmetrical midpoint between the two observers. Like, because that's exactly how they had to try and answer the Wang interferometer. They have to establish an interferometer that's stationary relative to the co-moving one and then they could take that fixed midpoint and make the motion relative to that on either end. And it's like, ooh, you guys are a bunch of freaking ether lads. Nice.
Yeah. I got to get me an outfit made out of space-time fabric. Don that bad boy.
So what about the interferometry that's done today? I've heard you mention it before, and they alter a lot more things to get the result they want.
Yeah. So a guy named Dayton Miller continued on the Michelson style interferometer setups for like 30 years. And he did all different kinds of experiments and configurations with them where he would use different heat sources to heat up the interferometer, take the measurements at different times of day for different ambient heats. He would use materials that had different magnetic properties. He would use different coverings, different shieldings for the interferometer, because you don't see it here, but there's a case that goes over this that covers the path of light. So you could use like an opaque wood, or you could use glass, etc. He had different frames and stuff that he would use, all different materials. And what he found was that if you do these experiments in a hermetically sealed chamber, so like a vacuum tube, and in a basement with like concrete walls, etc., below sea level or at sea level, you're going to get the least amount of change possible. So when they do these measurements now, right, the ether drift that goes through the apparatus isn't able to produce any of the magnitude of the measurement of that difference when it recombines. So they take it as right. Yes, the friendship. So they take that as like, oh, that must mean the speed of light is constant in the east-west directions and in the north-south directions. And actually, a guy named Demjeminov came along and did a bunch of experiments as well, using different, like similar to how this guy had a tube of water here and a tube of air. So this Demjeminov guy was using different refractive setups, or different mediums and stuff, and showed that basically if you use a vacuum chamber you're not going to get the same amplitude in the fringes because there's not enough ether in there to like, it's going to make it appear lower, and you're going to like register it out as like, oh, this isn't significant. But when
Because
you add
they want no fringe shift for
right.
Einstein's theory.
Yep.
Right. Okay. Yeah.
Yep.
So Vanby, you were asking about the Sagnac effect. Alan, that Sagnac effect, just doesn't it describe the phenomena of the phase shift and light beams that are traveling in opposite directions in a closed loop? Is that how they're using Sagnac effect? That's what they're referring to, the actual phase shift.
Hang on one second.
Oh, when they spin the interferometers with.
Yeah, and an enclosed.
Sorry, I was reading something. Okay, yeah. So, what was your question? Sorry.
It's just that Vanby was asking what the Sagnac effect was earlier.
Oh, the Sagnac effect is when a split beam completes a circuit clockwise and counterclockwise to itself, and it's out of phase proportional to the velocity of the rotating apparatus.
So yeah, that term is describing the phenomena itself of phase shift in light beams traveling in opposite directions along a closed loop.
Yep.
Okay.
And then he had like a little miniature setup of this, and it just turned faster. It was essentially this, but instead of being in a cross configuration, it just makes he made a weird polygon shape. But yeah, just a closed circuit, and then it just rotates. But I think he was rotating
thereby inducing phase shift.
Yeah.
Yeah, got it.
Right. Okay.
Yeah, because this one rotates, but it rotates hella slow. You just baby turn this very gently, like Sagnac had a rotor.
But it wouldn't be rotating while they did the measurement.
Yes.
Oh, it did.
Mm-hmm.
Okay. Gotcha.
Mm-hmm. So what they did is they had a lab assistant with a little stick and the little micrometer wire hanging over it. They had a lad with a telescope on like a basically like a, I don't know, like on a stool with wheels, I guess, and he's like following with the eyepiece, and then dude's marking where the fringes are with the micrometer. Dude's like, okay, you got it marked. And they're marking it on a sheet, and then they go and measure it, when they take the sheet off where the guy was marking it.
Nice. Cool.
So why did they, sorry if this is a dumb question, but why were they rotating?
Great question. So that is a manipulation of one of the variables. So it would be the way that the configuration is set. It's they got east arms and north-south arms. So that we were looking for a difference with respect to the time of day and direction. So if they're like basically trying to see like what direction the ether flow is, what's going to get the best magnitude for it. So if they're looking for variations with respect to the orientation and time.
Oh, gotcha. Okay, that makes sense.
Mm-hmm. Yeah. Alrighty. Well, I think that's a pretty broad overview of the history of interferometry and the implications.
Thank you. That was cool.
Yeah, that was sweet.
Yeah, no worries. Say hi to the YouTube lads. I'm gonna end the recording.
What's up, YouTubes?
See ya, YouTubes.